Thank you for the recorded catch, though. I have it recording now. So, yeah, I'll just write bigger from now on. So we'll have the minus 100 3 feet, or minus 100 pounds times 3 feet. That comes from here, going from C to D. And then we're going to have our components. And for this problem, since we don't have a vertical dimension for BC, we can actually do something tricky with angles. We can say that there is an imaginary line like that, and that we have this angle theta. That angle theta. And so with that, we can actually say that sine of BC is this. This is going to be our sine theta times BC. And here, this is going to be our cosine theta times BC. To see clearer, hit on gallery view and pin the video. Okay. So since we know we can break up BC into these components using theta, we can say that our I'm going to need, yeah, I actually can't be in full screen because I need to have this up too. But yeah, if anyone else, apparently you can go to gallery view and pin the video and it's clearer. Okay, quick correction though. When using our sine and cosine like this, sine BC for the vertical component and cosine BC for the horizontal component, we're not going to do, okay, I understand why they do the order they do right now though. Okay, we're gonna have to backtrack just a bit. And actually skip to this cut. Because we're going to need this tension before we can actually do the center. Or do we? No, we don't actually. Sorry, I keep lying. Yeah, to avoid confusion, then let's just keep going the way we were doing it. Where we have our cut like this. Here we have TBC. Vertical component, X component. And we have $100. With these components broken up into cosine and sine, we're not going to be able to work with the moment equation since we're going to have two unknowns in the one equation. What we can do instead, though, is we can write some of the forces in the y direction equation, which will include this, and dy, and we'll have some of the forces in the x direction equation, which will be a TBCx and dx. And that would leave us with two unknowns and two equations, both the unknowns being TBC and theta. So well, sum of the forces y is equal to BC sine theta, and we're going to have equal, which we know is 77.9. And then we're going to have some of the forces X. This is equal to 0, of course.
Minus 100, right?
Yes. Yes. Sorry. Minus 100 pounds equal to 0. So some of the forces X is going to be X component of TBC. Since we assume tension, that's going to be left. So we're going to have to say minus BC cosine theta. And then we know dx is going to the right. So that's going to be plus 41.2. So what we can do now is we can actually divide these equations. So we can say some of the forces y divided by some of the forces x, just like this. And what's going to happen here is, well, you would want to move these terms over before you do this. So we would say this would be minus 77 and plus 100 because we moved it over, and minus 41.2. You do this so that you can actually divide, because if you have them all together, the fractions just don't work that way. So we separate the BC sine theta and the BC cosine theta on the one side, and all of our actual known numbers to one side. And then once we know that everything is separated and we do our division, BC is actually going to cross off here. And this sine divided by cosine is just tangent. So we'll have tangent theta is equal to whatever this side is, which that would come out to be, could you do this real quick?
Yeah. 77. Well, that would be 22.1 on the top for sine.
Okay.
41.2, right?
Mm-hmm.
Inverse tangent.
Right.
0.49.
Oh, for this,
Yeah,
and then inverse tangent of that.
yeah.
Oh, okay. Wait, what? Oh, degrees.
For the degrees, right?
Yeah. Is sine always with y and cosine always with x? Can you do a quick review on how to distinguish which to use? Yes, I can. So I'll take this other space over here to explain this. So when you have a triangle, right? And I've chosen this triangle because it models the triangle that we have for this problem. So we have a triangle that looks like this, translated over here. And this is our angle in question, right? Here we have theta. So sine from this angle, what we know about sine is equal to opposite over hypotenuse. That's what sine is. So sine is going to be y. I'm going to call this c. So if you want the vertical component for a triangle like this, you would say sine theta. Cosine is over hypotenuse. So that would be x over c. So if you wanted the adjacent side for a triangle like this, you would use cosine. However, this changes depending on, I want to make sure that they can even see this. Yeah, they can, okay. This changes depending on how your triangle is oriented. And so that's why I always say to think about it in terms of it's like a trig meaning and not that sine is vertical, cosine is horizontal. Always think about it, the sine gives you the opposite side from your angle, cosine gives you the adjacent side from your angle. Because what happens is, if we have a triangle that looks like this, and here's our theta, sine on this triangle is this side. So sine is going to be our x component. Sine for a triangle like this, you'd have sine theta times, this is your tension value, times this tension is going to give you this component, which is x. So depending on the way your triangle is oriented, sine and cosine can give you different components, x or y. So it's always important to draw out the line in your problem and recognize, okay, I have my angle here. The side I'm looking for is over here. So which trig function do I need? I need the one that gives me the opposite side, sine. Oh, I have my angle here. I need the x component here. It's next to my angle. Which trig function about the trig functions and how to know which one gives you x and y. Does that clear things up? Awesome.
I got a 28.21 for the.
Okay, great.
Sorry,
No worries. 28.21. Okay. Yeah, when you said 0.49, I'm like, time to recognize, so that's really small for degrees. And that is, I believe, exactly the angle they get. Yeah, they also get 28 degrees. Awesome. So now that we know our theta value, which again, we got our theta value from dividing our sum of the forces in the y divided by our sum of the forces in the x. That got our BCs to cross off, so we just had tangent theta is equal to the constants. And now that we know theta, we can actually say BC cosine of 28 degrees is going to be equal to minus 41.2 pounds. We can just plug in our theta value where we got it and we can find BC. So BC should come out to be 46.7 pounds. Oh, this was minus BC. That's why it works out this way. I was like, we shouldn't be getting a negative answer. Yeah. So this was minus BC since it was going to the left, and we had plus 41, but we move it over, so it becomes minus. So we had minus equals a minus. So that's why we get 41 or 46.7 pounds in the correct tension direction that we assumed. And so now that's our BC. So we can go ahead and solve for our last unknown TCD. And this is where And if everyone's all right with it, I'm going to erase this just so I can keep writing larger. If you would like me to keep it, just say something, or if you, okay. All right. So with our diagram, once again, we're going to keep going. And we finally, at last, just have joint D with T CD as our only unknown because we've already found dx and dy. So here we can easily just say sum of the force in the y direction is equal to dy 77.9 minus, we say minus because TCD is going down and to the left. So minus TCD times the y component ratio. CD, we know the height is 3 feet, and we know the x distance is 3 feet. So square root of 3 squared plus 3 squared, not square root of 18, because so we know that this distance is going to be square root of 18 because we have 3 and 3, that's 9 and 9, add them together, square root of 18. So our y component ratio is going to be 3 over square root of 18. And that's it, because all we have is these three things with both of these being known. So we can just go ahead and say that T CD is equal to what was it, 88.2 pounds. And we get a positive answer, so our tension value is correct.
How did you get the vertical component real quick for that last note we were doing?
Oh,
You said sine, but I remember solving to get 3. Oh, 7 minus 4.
yeah,
Okay,
sorry. So we know this that 7 is from A to B, and we know that 4 is from A to D. So D to B must be. Oh, that's not the whole length, is it? No, because that would only be from D to B, not all the way down from D to C. So we actually got to make that correction.
That's way too easy.
Well, actually, it's even easier than that. Yes. So just been saying that TCD is equal to the square root of dy squared plus dx squared, because at this joint, this resulting force is going to be the hypotenuse of these two components. Forces. So, so knowing that, we can just say that TCD, yeah, there's so many letters. TCD is 88.2 pounds. And so using things like the tension is equal to the magnitude of these reaction forces, and like using this theta method is a way that you can get around not having the dimensions given to you. So if at any point you're working with a cables problem and you're like, man, I could do this problem if only I knew the dimensions, try out some kind of other method like this or like that and see how that can help you get through it.
Yeah, are we done with this question?
We do have to find L total still, which is the last thing. So for this problem, the total length of the cable we know the total length of this cable is 65 because we've already found it, right? So L total is going to be equal to square root of 65, the length from A to B, plus cosine theta times 5 feet, because cosine theta of this, cosine theta, sorry. So we would have cosine theta is equal to 5 feet over the length that we want, which is going to be BC. Because cosine is adjacent over hypotenuse. Our adjacent length is 5 feet. That would go from here to here. And this unknown length is what we're looking for. So BC would be 5 over cosine theta, which we know theta already, but I erased it. But I think that theta was equal to 20. Yeah, 28.2 degrees. So BC, if you could do this. So we have the length of AB, we have the length of BC, and now we just need the length of CD, which for this one, because it reacts opposite to resultant forces of dy and dx. Yes, exactly, for TCD, that's exactly correct. Okay, I'm just reading how they get the distance for the last piece real quick. Okay, so did they just like not explain this?
Wait, what are we trying to do?
The length for, so we have this length and we have this length, and I'm looking for how they solve for CD, and I think I actually just found it. So
theta.
Where they say, yeah, so that's exactly how they do it. So as you guys can recall, we have our dy and our dx values right here. So we can say dy looks like this, and dx, we know to the correct. We can say that it is 77.9.6.9. And then our dx, we can make it like this, because you can imagine like that. So that's going to be the 41.2. And I'm using pounds as a unit of distance right now. So we can take, and then we would have like this, right? So we could find this angle, this new unknown theta. I'm going to call it theta 2, just so that there's no confusion. By doing tangent, because tangent is opposite over adjacent. So tangent of theta 2 is going to be equal to the 41.2 divided by 77.9. And theta here is going to be equal to okay. All right, it's fine. So theta here is going to be equal to, if you could do this.
Inverse tangent,
Mhm.
27.87.
Okay. So what we have done by finding 27.87 degrees is that we have said that this angle here is theta 2 is equal to 27.9 degrees. And with that, we can actually say that a trig function of this angle times sorry, not either, because we don't even have this full for the dimension. But so what we can do is we can say come over here. I want to make sure that you guys can see. Yeah. So what we can say from this, knowing this angle now, we can say sine of this angle, because sine of theta 2 of 27.9 degrees, this is going to be equal to opposite over adjacent. This opposite side, which we know is 3 feet. So this is going to be equal to 3 feet over our unknown. I'm going to label this. That was wrong. So as x. So therefore, divided by sine, because we multiply x over and then divide by sine of 27. I can write it in a better way than vertically. So we know theta 2 is 27.9 degrees. And we can say here, sine of that angle, sine of this angle right here, which we found using dy and dx, is going to be equal to the opposite distance, 3 feet, over the unknown distance that we're looking for, x. So divided by sine of 27.9 degrees. X being the length of CD. And then if you could, sorry, you're like my calculator guy, but
6.41.
okay. Okay, so we found the full length for CD. So we can say L total is equal to all three of these things added up. Do you mind?
Yes.
If we have a question that takes this long on the exam. Yeah, the thing about the exam is that it should be very similar to the last one, where you only have like a few questions. I want to say like 4 or so, if that's because you guys only had like 3 or 4 questions on the last exam, something like that. It will be very similar again. So you're not going to have like 8 or 10 questions to get through that. Oh, 20.13. And that's what they get. So that is your TAB, TBC, TCD, and L total. So just a recap of it, what we did is we took a cut and we took the right side, moment at D, to solve for these unknowns. Then what we did is we took a cut here, took the right side, and we did some of the forces in the X and Y direction for finding, and use those, divide them by each other to find our theta here, replugged the theta back in for one of our equations, and we solved for TBC. Then we moved our cut over once more, and we found TCD as the resultant of dy and dx. And then finally for our L total, we found the length for AB, for BC, and then we used an angle here with these forces to find this distance, and we add those together. That is our L total.
So when you want to find the theta for that last one, I do like a triangle from the inside.
That's totally fine.
Okay, so you just kind of go about it a different way than if you have from the inside.
Right. So if you what you're saying is you drew your triangle like this.
Yes.
Okay, that's totally fine. So if you were to do it like this, your 77 would be on this side, your 41 would be on that side, and the angle you would be solving for would be right here.
Okay.
And so then when you use that, sure.
All right, so basically what we did was you took a cut at AB,
Here.
right? And then you took
Yes.
a moment at D, and then you found AB, and then you used that to find dy and dx.
Yes.
Okay, but what if it didn't give you the vertical component of AB? If it didn't give you just from A to B is 7. If it didn't give you that 7, can you still go ahead and do the cut since you don't know the components of it?
So you're saying this same exact problem, except they don't give us the 7 feet here?
Right, all the 4 feet.
So if you don't know any dimension for AB,
then you couldn't make the cut then, right?
Right, you couldn't do your cut there because you wouldn't have anything to work with.
Okay. Yeah, I think this
You
is
would,
like that.
I believe what you would have to do is you would have to start over here like we did. You would have to, so if you didn't know any dimensions of AB, I think that you could at the beginning take moments at A and D to set up equations where you can do a moment and have an equation with dy and dx and an equation with ay and ax. And then you would also have to do your sum of the forces in the x and know that ax and dx are equal to each other. So you can substitute them. And you could also take some of the forces in the y direction and use ay and dy. And then you would have, after doing 2 moment equations and your x and your y component, you'd have 4 equations and 4 unknowns. And you would have to solve like that through systems of equations, like by substituting and stuff. And then you would have to start with this theta method that we used before after finding these in the beginning. And then you could know CD, and then you could do your cut. So you would do your cut here, you could know CD, then you do a cut here, and then you would know BC, because assuming they still give you all of these dimensions.
Okay.
And that's how you would have to go about that.
Okay. Also to find DC, last question, to find DC, we know A to B is 7, right? And D to B is 3, right?
Sorry,
So,
say again? You know that we know that from A to B is 7.
right. And the distance from A to D, the vertical distance from A to D is 4, which means D to B is literally 3, right?
Yeah.
So we could use we could find the vertical component of BC, right? And add it to the 3 to get the
Yes.
vertical.
You
Then
could do
just
that
the
as
square
well.
root of that, and plus 3 squared, and then you can find DC, right?
Yes, you could do that.
Okay, thank you.
So yeah, this problem did take a while, but a lot of it is because like I would stop after writing stuff to talk about it and explain the concepts. You guys are gonna have to do the problem faster than I did, of course. And so when you guys do the problem, you can just have a checklist in your head of, okay, what do I have? What do I need? What am I looking for? What kind of methods do I have to approach this? And you just have to try to start doing some of those methods and not stand and talk and explain them, of course. But yeah, enough practice and enough seeing these kinds of problems, you guys will get faster at them. So if you're worried about time, just keep doing practice problems. Yes, I promise. Any other questions on this problem? Can we do some on friction and compare the different types of friction problem? Yeah, so I believe we can do trusses 2, problem 1, and then we can do a friction problem. Someone had requested that. Okay, trusses 2, problem 1. Oh yes, zero force members. Okay. So this is trusses 2, problem 1. So for this problem, we're going to need to identify all zero force members and determine the forces in members J, E, GF, and JF. So we have a structure. This A, B, C, D. Okay, so this problem wants us to, and I believe I have another marker that would make this easier to see. So this problem wants us to find JE, wants us to find GF, and JF. So what we're looking for are the tensions in these members, and we're also looking for all the zero force members. There are 2 loads, one here, 6 kilonewtons, and one here is 6 kilonewtons. We're going to have support, and is that a roller? Yeah. Okay, so what we can do first right away is recognize that when we take our cut here, we're going to need EY. So we can say that we're going to take the moment at A and find EY. So if we're going a counterclockwise moment around A, we'll see that our 2 6s go with that direction and our EY goes against it, goes up and the 6s go down. So we'll have plus 6 times, I didn't draw any distances on here. This is all 1.5 meter. They're all the same. And the total height is 2 meters, 2 meters. So this is going to be 6 times from G to A. That's 3 meters. From F to A, that's going to be 4.5 meters. And then we have minus EY times the full distance of what the heck? 6. So then that's the whole equation. And we would say that EY is equal to 7.5 kilonewtons. So that's our support. So I'm just going to write up here that we know that EY is equal to 7.5 kilonewtons up. And before we take our cut, we can do the zero force member portion first. We can find all of which members are zero force members. So let's take a look. Here at H, can see there's no force applied down. And if we look at just H, it has this kind of shape. So a force moving by itself here in the y direction is automatically going to be 0. So we can say that this is a 0 force member. And what we know is that if H is a 0 force member, and we go and we look up at I, or if HI is a 0 force member, we go and we look at I, and look at I shape. What we actually do is we can turn this shape to look like that. All this is I took this shape and I turned it. And if we look at that, we have the same kind of shape. These are going to be equal and opposite, and this is going to be 0. So no, this is 0. Then additionally, if we go up and we look at joint B, if we look at this joint, we can see we have this kind of shape. And this is B. Here, we can see that in both the X and the Y direction, these are the only forces. So we can immediately say, because if you were to write out some of the forces in the Y direction, you would only have so then on the other side, we can see the same thing happening at D. So we can automatically know those are both 0. Except now, when we go ahead and we look at F, we can see that there's an applied load here. So when we take our F joint, JF is not going to be 0. And because of that, JG is also not going to be 0. Because we only could say that IG was 0 because we knew that HI was 0. And those are all of our 0 force members in this problem. JG is not 0 because FJ is not 0. If FJ was 0, JG would also be 0.
I have a question.
What's up?
So the forces of like AX and AY that are there because of the pin, those don't affect like the force number from A to B.
So that's a good question. So if you were to take your cut at A, it would seem as though they would. However, if you look at the other side of this member and you go up to B, you can write it as just this. This is joint B. And think of your method of joints. If this is B with 2 unknowns, and we were to say some of the forces in the Y direction here equal to 0, it's going to be equal to BA. And that's it. That's the whole equation. So even though on this side, where there's a bunch going on, if you can identify one side of the member where you can assume this, then it's going to be a 0 force member.
Okay, thank you. Yes, yeah, thanks.
You can go ahead and find the unknown internal forces. From this point, seeing that we're looking for this member, and this member, we can go ahead and make our cut like this. Capturing our new diagram would look something like this, where we have, I don't know, is this too low? Where we have EY, we have -6, and then we have all of our unknowns, where we have TDE, TJE, TJF, and TGF. So what we know right away about at least one of these we already found EY before, remember? And we can go ahead and take a moment to cross off one of the, or cross off two of them. We can either take our moment here at F, or we can take our moment here at J. And I just want to take this chance to reiterate what I said earlier about if you guys are doing practice problems and like know how to approach it, and doing a problem on the test is going to be much quicker than my explanations of these, because just me drawing this, I've taken like 5 times as long as you guys would take to write that out. To see these, know that you take your cut there and write that. Whereas I'm explaining why I'm taking the cuts, why this goes away, et cetera, et cetera. So that time adds up in my explanations. And so don't feel like time is going to be huge because of time. Yeah, you have to know it. You have to be prepared, of course. You do have to be prepared, of course. But I'm just emphasizing that I'm purposefully taking longer than you guys should take on these problems. So we'll take our moment at F or our moment at J. For this one, I'll say that we can take our moment at F, just for the sake of it. So let's say a clockwise moment at F is going to be equal to, we can see right away that our GF, our 6, and our JF are going to all cross off. So the only thing we'll have is JE and EY. So let's go ahead and say minus EY, which we know is 7.5 kilonewtons. We say minus because it's moving up and we've assumed a clockwise moment. So when it comes around to the right side, that direction is going to contradict our moment. So that's going to be 7.5 kilonewtons times 1.5. And then we need our components for JE. So doing the components for JE, we're going to need Y and X. For the X component, it's going to go from E and move to the left, since we've assumed up and to the left as our tension. So the X component is going to pass through point F and cross off, not be included. Because you can see that like this and like that. This X component will pass through the point that we're taking the moment about, which is F, and not be included. We know that the dimensions for JE is X 1.5 meters and Y 2 meters. So the hypotenuse for JE, this distance, would you mind just doing a square root of 2 squared plus 1.5 squared? You're good, don't worry. Okay, so we know that the distance for JE is 2.5 meters. So our Y component, the one that we're looking for, is going to be 2 over 2.5. And then the there we go. Sorry, because this is for EY and this is for our unknown. Because EY is going to be those 7.5 times 1.5 meters. Our unknown JE is going to be 2 over 2.5 times TJE times the distance from F to E, which is the same 1.5 meters from here to here. That's where we get this equation from. And what we're doing with it is we're solving JE. So TJE should come out as 9.38. 9.38 kilonewtons. And this comes out to be a negative value, because when we move this over, this side is still going to be negative. So our assumed tension is backwards, and we will say compression. So we found our first piece, TJE is equal to 9.38 kilonewtons in compression. What did I do with the cap? It's on the back of it. So now that we know TJE, that one's done, we can go ahead and just do some of the forces in the y direction. It's equal to 0. This is going to be equal to EY. We're doing some of the force in the y direction to solve for TJF, because now in the y direction, this is our only unknown. So we'll have plus EY, 7.5. And we'll have, we know that TJE is minus. We know that it's actually compression. So I'll go ahead and rewrite our arrow going the correct way. So we'll say minus TJE, which was 9.8 times the appropriate vertical ratio. We know the 2.5. And we'll have minus 6. And then finally plus TJF. Use this equation to get that TJF is equal to 6 kilonewtons. And what's funny about this is that we could have from the very beginning known that these two things were equal to each other, because we just did an equation that said that. So this is really the only part that ended up mattering. For the sake of it though, you can write out the whole thing. We get a positive answer though. So we say that TJF is in tension. I'll go ahead and say. So that's where, what's up? And now, last but not least, we can do sum of the forces in the x direction is equal to 0, equal to minus TGF, and then plus, because we see that TJE is going down into the right, plus our value for TJE, and that would be all of our x direction components. So we would say TGF is going to be equal to 5.62 kilonewtons. We say in tension because we get a positive answer, so our assumed tension is correct. Any questions on this problem?
May I just start here, but I ask a question?
Sure.
How do you do zero force bending? Like, how did you?
Okay, yeah, so that part was pretty quick. I'll go over it real quick fast again. So when you have a, I'm not going to erase this yet. When you have a zero force member, right, what that means is that that member has a joint where you can set up an equation to prove that it's equal to 0. That's how you can like know for sure. But the shorthand way of writing that is, I'll start off with joint B, right? So if we say joint B, right? And we model this joint, so we say we're going to take a cut like that. That's it. There's no applied load. Direction equal to 0. You would only have the BA cut here. And that's it. So you know, right, you can do the same thing. Some of the forces, oops. Some of the forces X direction equals 0 equal to BC. And so that's how you would prove that they're equal to 0. However, the goal is that you don't need to go joint by joint to say that these are equal to 0. So you can just look at B and see that there's, you take this joint, there's nothing else going on there. But then finally down here, right, we have joint H, where if you were to take your cut, you can see in the Y direction, this is your only thing going on. There's no applied load down here. So this must be 0. And then the only tricky part for a zero force member is where you have joint I, right? So we have joint I. And what it is it looks like this, right? What we can do is we can take this and we can turn it and we can make it look like this. So all this is me taking this shape and putting it like that. And if we know that this is 0 already, what do we have now? We have this. We have that shape. So therefore, this member must also be 0, which is this member, which is here.
So how did you determine that?
So we determined it was 0 because we already know that HI is 0, right? So when we have this shape where these two members line up, and we have a member coming out of it like this, you can turn it and make it so that your new Y direction has these two members. Well, we know one of them is 0, so we can just get rid of that. And if that one that we got rid of is 0, the only one left must also be
Yeah, it's
0.
There's no forces applying in the
Yes. Yes, in our quote unquote Y direction, when you turn the shape. That's how the zero force member works. We can see that that's not the case at F, all because of this load right here. Because of this load, Fj is not 0 because of this load. And if Fj is not 0, Jg is also not 0, because when we turn our shape, there's going to be more than just Gj is equal to 0.
What if we do that in joint G? There's joint G, there's Well, you said that one, the one is 0, but if you do that, joint G, there.
1, 2, 3 unknowns there and 6 kilonewtons applied. So there's a whole bunch of stuff going on here, right? But we can take that same concept and apply it over here at A. At A, if we take this cut, we'll have 1, 2, 3 unknowns and AX and AY to top that off, right? However, the other side of this, B, has nothing. So because the other side of this has nothing, this is still 0 force. And so even though there's a bunch of stuff going on at G, IG is still 0 force because there's nothing at I. So checking both sides,
For the simpler side.
yes, the simpler side will usually show you that it's 0. If it is 0, it's going to be 0 at the simple side. So that's where that comes from.
Can you only do that because it's like symmetric, or is that you're able to do that?
Applicable anytime.
Thank you.
You're welcome. Okay, so we still wanted to go over, what was the next question? Sorry, whoever, oh, there, can we use some on friction? And yes, yes, we can do some friction. Okay, so let's go ahead and do problem number 3 in the exam review. Your camera is off. Oh, what? How did that happen? You messing with my computer, Raleigh?
I'm hoping it's recording at least.
Yeah, it's still recording. Okay, sorry about that. So we're given a shape. It looks like this. At the other side of it, this is just the left side view. So these are the same. We know that this is 1 inch. We know that this is 2 inches. And 6 inches. And then we have force F somewhere like this. And we know that this is 4 inches.
This is F like that. It's basically the same thing as P.
Yes.
I don't know why they switch up the letters.
Yeah, P or F or whatever. And then they say that this side is A and this side is B. So the problem wants us to determine the largest force F to cause impending motion. They say that this is a 20-pound object. So this is 20 pounds in total. And is supported at A and B, the distance H and, okay. So they tell us that 0.4. and it wants us to determine the largest force, F, or to determine the force that would cause impending motion. So we need to test for slipping and tipping, or sliding and tipping, slipping or whatever. So what they do first is they take a look at the volume so that they can distribute the weight of the shape between the large rectangular section and the smaller triangular section, because the weight for the large rectangular section is going to be somewhere in the middle here, like this. The triangular section, that weight is going to be skewed towards the peak. So we're going to have two weight forces like this. So what they do, the volume is equal to, we have all the dimensions, I think. Yeah, this is 4 inches. And with that, we have all the dimensions. So we would say the volume of this shape is going to be 4 times 4 times 1, because we know that it has a 1-inch depth into the board here. Sorry, that should be 6. 4 times 6 times 1. Whatever. There we go. So 4 inches times 6 inches times 1 inch. And then we have the triangle, which is going to be 2 inches times 4 inches times 1 inch. We'll have half the volume. Yeah. So the total volume here is going to be 28 cubic inches. And with that, what we can do is take the 20 pounds overall and divide by the volume to get a unit weight. So we can say the unit weight is equal to 20 divided by 28. This is 20 pounds over 28 cubic inches. So the unit weight is 0.714. And with that, we can multiply by each side of the volume, right? So if this is just 4 times 6 times 1, we can wait for just this piece by multiplying this by the volume of this. And the total.
Point load, kind of?
Yeah, yeah. We're turning the weight of this rectangle into a point load in the center, and the weight of this triangle into a point load skewed to the high side. So I'll say that V1, this is going to be V1, our 4, which is 24 cubic inches. So our unit weight times this volume is going to give us the actual pound value for the rectangular section. So 24 times 0.714 is going to come out to be 17.14 pounds. And that's here in the center for the rectangular shape. The triangular weight is going to be V2, which was 2 times 4 times 1 times 1/2, which is just 4. So this 4 times 0.714 comes out to 2.86, and it's skewed to the high side. How much is it skewed? It's skewed 1/3 from this edge, or 2/3 from this edge. So the distance from the very edge to the weight of the triangle is going to be 1/3 of 4 inches, which is, so that's how we get our weight values. Knowing our weight values now, we can begin our test for sliding and tipping. So let's say sliding first, or slipping, whichever one is fine. So for this shape, we're going to have our normal force in the center. We're going to have our F, and we have our F here. So
I think there's 2 normal forces,
yes, there are. Thank you.
and one goes away if it tilts. I remember that.
That is the case, and that will be important for the tipping section. So for here, we're going to have NA and NB because it is supported at these points. And so we're going to have a bunch of F values where we say in our equation, based on this, I have to say sum of the forces in the x direction is equal to 0. And that is going to be equal to our F, because it is in the x direction. And that's going to be minus the friction A, because they say FA. And they say like this, that you also have the FB. And that this, you can rewrite this, you can change these like this. And then finally, they say, whoops. So what we've done here is we've taken a sum of the forces in the x, which is F, F, and F, and changed our FA and our FB to be mu sub S. This is just universally true, that the friction is going to be equal to mu sub S times N. This F is friction. Yeah, and this is all equal to 0. And now that we have this equation, we can say sum of forces in the y direction equal to 0 is going to be equal to plus NA plus NB minus 17.14 and 2.86. That's actually just our original minus 20 that we had in the beginning. But for later in the problem, it's relevant that they're splitting up. So for this, we can just say, okay. So for this, we can just go ahead and say that NA plus NB is just, but now that we've said this, we can actually replace this here, and we can say 0 is equal to F minus mu sub S, which is known as 0.4, times NA plus NB, which we know is 20. And looking at our equation, that's it. So we know that F is equal to 0.4 times 20. So F must be 8 pounds. And we found our F for sliding. So our F sliding is going to be equal to 8 pounds. Any questions on how I found the sliding F? No? Chat?
So for like the force of A, is it always just going to be like the friction constant thing times the normal force of A?
You mean for FA?
Yeah.
Yeah, so basically
Or
what we did, all we did was we substituted our friction A's. This F is FE is this FE. And so these become mu sub S times N. I could have written it mu sub S times NA plus mu sub S times NB, but I just had it like this for the sake of this easy substitution. So always your friction F is going to be equal to mu sub S times your N. Your friction at A is going to be equal to mu sub S times NA. And FB is going to be equal to mu sub S times NB generally.
yes, yeah, I hadn't seen like the equation on the top left, but yeah, that's helpful.
Oh, this?
Thank you. Yeah.
Yeah, this is important. Yeah, this is important for basically all of these friction problems.
Thank you.
You're welcome. So now that we've tested slipping, we can go ahead and test tipping. So for tipping, we're going to have to say that at that point that F causes it to slip or to tip, that the normal force at the point that leaves the ground, in this case NA, because you can see as the force pushes this way, the shape is going to want to move like that, and N and point A will no longer touch the ground, because as F moves this way, our shape is going to want to do this. It's going to fall over. So this point, NA, is no longer on the ground. So NA goes away. We don't have to worry about it for tipping. So what we can do, now that we know that NA goes away and that the whole structure tilts, is we can say, taking the moment at B, we'll get NB and FB to cross off. We know that our FA and NA go away because this point leaves the ground. So this is going to be equal to 0, which is equal to the counterclockwise positive, so we'll have minus 17. And this is why splitting it into pieces becomes important, because this weight is at a different location than this weight. So if the entire thing were rectangular, you wouldn't have to worry about splitting it. But because we have a different kind of shape here up here, these like centralized weight, when you turn it into a point load, is going to be at a different location. So we have minus 17.14 times the distance, and we'll have minus 2.86 times the distance to this point, which we know if this is 4/3 of an inch, this distance from here to here is 4 minus that. And then we have F, where F is moving with our moment. As the moment moves this way, we can see that F, they line up. So we'll say plus F. times a distance of 4 inches. And so with only one unknown, we say that F is equal to 10.5 pounds. Slipping and our F tipping, and we can see that our F slipping value is much lower. It's 8 compared to 10.5. So this will happen first. And that's the whole problem. That's all you have to say for this one, because all they wanted us to do was to find the forces at which motion would start and to confirm which one would happen first. We found our F for slipping, found our F for tipping, and we can see that 8 is the values in the box at the bottom on the paper, but just say that this is the one that we care about. Any questions on slipping or tipping?
How did you get the 4/3 inch one more time?
Oh, so this distance is just 1/3 distance of a triangle. You can think of this as a distributed load, right? We can think of it as though it were this. And if this entire force, we make it into a single point load, this is going to become this. Skewed to the larger side. So that distance is 1/3 of this whole distance. So it would be 8/3, but that's where that comes from. Could you do a pulley problem after and explain how to determine the radian beta? Yeah, so I will say that in lesson 27, where the exam review is, I believe that I go over problem 13, which is the belt fix friction, onto the LA page about that exact problem. And that shows you how to do the radian beta. But if you guys want, I can go over it here again.
If you did it already, I'll just go off that one.
Okay. Okay. No worries, no worries. A friction problem with the weird tractor things or internal forces. What do you mean by weird tractor things?
Oh, the tractor pulling the crate.
There's those ones where it has like,
Oh, yeah.
like a
Oh,
dump
there's one
truck
where
or
it's like it's
something.
pulling a crate, and there's one where, yeah, it's like pushing a log up a hill.
Okay. Do you have like an example problem for that?
I think it's in the friction.
Yes, hold on, let me see.
There's on friction 2, it's the second problem.
Friction 2, second problem? Okay.
That's the one the tractor pulling something, but then there's another tractor one. That one's in the friction. Oh, it's a truck, not tractor. Okay. I'm assuming they're talking about friction 2. Problem 2.
I'm getting friction 2, problem 2 pulled up right now. Does that problem work for you?
Yes. Yeah, that's good.
Okay. Okay, I've got it up.
Oh, I know this. Yeah, that one, the one that's pulling it crazy. I was looking for the one where it's like someone's like pushing a log up the hill.
Oh, I think that is friction 1, problem 3.
Okay, okay. So
Yeah.
in this problem, this is friction 2.
Oh, okay, yeah.
Problem 2. There's a tractor pulling this box on the ground. And so we know, what we know is that the radius of this tire is 0.8 meters. And we know that the distance from this point to the ground, this distance in between, that is going to be 0.4 meters. And we're given the coefficient of static friction between the tires of the tractor know that this tractor weighs 1,000 kilograms. We know the crate weighs 450 kilograms. Am I sharing my screen? I'm just writing the problem up here on the board. The problem, you can't see the camera?
I can see it.
Amanda, you can pin him because sometimes because he's talking, it'll show just his name. So if you look up where all like everyone else's name is and find his camera, you can click it and pin it, and that'll bring up the main screen, the whiteboard.
You did and it's not showing up? Okay. I'll let you back in right away. Okay, can you see the board now, Amanda? Okay, awesome. So we have the tractor pulling the box, and we have the weights, or we have the masses of both, and we know that the system is starting from rest. What torque must the tractor's engine exert on the rear wheels to cause the crate to move? So what we need to do first is we need to find the force here that's going to cause this crate to move. And then we can take that force and turn it into the torque needed for the tractor on the tire. So we can go ahead and say that our free body diagram of our crate, oops, this is FBD of crate. That this crate is going to have a force here distance being 0.4 meters. It's going to have a normal, and it's going to have a weight in the center, which is 450 times 9.81, which is going to come out to be 4.41 kilonewtons going down. And once again, this is just the mass times 9.81 for gravity. So having this equation, what we can do is we can actually do the so my immediate thought was to take a moment at this point, but if we do that, you can notice that N, F, and the weight are all going to go away, and we will just have an equation equal to F. Well, this is going to be equal to minus kilonewtons and plus N. So we know that N is equal to, so then we can say that our FC, our friction, is equal to mu sub S times N. And this is that same equation coming back from before, where we have friction is equal to mu sub S times the normal force. So this is going to be equal to 0.3 times 4.41 kilonewtons. So FC, I'm just calling this FC, comes out to be 1.323 kilonewtons. So that's how we know FC. And then now that we have solved for our N and our FC, we can say some of the forces X direction is going to be equal to FC, which we know, plus F. FC is going this way, my bad. So F is equal to FC. So F is 1.323 kilonewtons. Yeah. And that's so the tractor is going to have its own free body diagram here at the wheel. Where we know that we have an F, an N, I'm going to just call this FA, NA, and we're going to have, we'll call this center point D, we'll have a DY and a DX, because this center of the tire has reaction, and we'll have an M, and we'll have the weight, and we'll have the radius, 0.8 meters. So here we have the free body diagram for the wheel, where we can say we need to solve for the friction here. So since we don't know the normal force, we can't use the equation of friction equals mu sub S times normal force. Because if we look, we have the weight, we have dy, we have NA, so we can't just say that the weight is equal to the normal force like we did for the box. So what we do instead is we take the moment about D. I want to make sure that they can see. They can see all the way out to here. Okay. In the moment here, we're going to have dy dx, the weight, and the normal force all go away. So we're just going to have the friction and the moment equal to 0. So we say moment d, and if we're going clockwise, we'll have minus fa times the distance here, which is 0.8. Yeah, sorry, this is dy and dx here at the center of the tire. On this tire, we have normal force, friction, dy, dx, the weight, and the moment d. So then, this is the free body diagram of just the wheel. We need now a free body diagram of the whole tractor. So I'm going to go ahead and write this over here. So the whole tractor more like a car, but it's a tractor. This force is this force in the opposite direction, pulling on the back of the tractor. And we have our FA, I'm going to call this FB. So friction at this wheel is FA, and friction at this wheel is FB. And we have our NA, our NB, because both of these points are touching the ground. And then we have the entire weight of the tractor, which is 1,000 kilograms times 9.81. This comes out to be 9.81 kilonewtons is the weight of this tractor. And so this diagram shows us the tension from here the same can do from this sorry, they don't have an FB because, yes, because freely moving. Exactly. This tire here in the front is not receiving any engine power, basically, because the problem specifically says, what force must the tractor exert on the back wheel in order to generate the torque? So there's no FB, but there is NB. So, but what we can do now here is we can say some of the forces in the X direction, and we can use FA and this force to solve FA, come back over here and get that moment. So FA minus 1.18 or 1.323 kilonewtons. So FA is equal to 1.323 kilonewtons. So all we're doing through these diagrams is showing that this force transfers to here, transfers to here. It's the same number continuously. And now that we have our FA, we can go ahead and move back over here and plug in for FA here and say that MD comes out to be 1.06 kilonewton meters. And I believe that is your final answer.
Can you remind me what the original question was asking for, like with the wording?
Yeah, yeah, sorry. So the original question, right here, the original question says, starting from rest. So starting from rest, what torque must the tractor's engine exert on the rear wheels to cause the crate to move? So we need torque on rear wheels. Very brief, discovering what force value would make the crate move. And then we take that force value and we transferred it to the back of the tractor, and then therefore to the friction on the back wheel through this equation, showing that this same force carries over. And then we took that force and we took it into the free body diagram of the wheel itself and found the moment needed at the center of the wheel to cause this force. And that moment that you found is the torque that you're looking for. Any questions on this problem? You sure?
Yeah. We need to know, like, tell them, like, I'm assuming, like, they would know which direction the wheel is going, right? Like, you don't need to put, like, an arrow to show, like, it's going forward.
Oh, you mean like that?
No, like, for, like, it's like the circle arrow, you know, like, show it's, like, which way it's turning.
Oh, so this circle arrow right here.
Yeah, for, like, not saying, like, for our answer, though. For our answer, do we need to, like, look
Yes, you
for the dx, dy, and the weight?
goes away. Doesn't matter. We don't care about it. It all goes away, including NA. A lot of these diagrams are redundant. As you can see, like this whole diagram and this whole diagram, like all of that, the point of that and why I took so long was just to show that F that you found here very quickly just gets put in for this. It's the same number. All you have to do is show that you're getting there.
Okay.
And that's another point of me saying that I take a long time showing these concepts so that you guys can understand it. On the test, you guys can do this, throw this together and say, oh, these are the only X ones, this is that, and substitute that in. All you have to do is know the method.
Okay. I think we can do this problem like that.
Right, but, you know, I'm just saying once again that
Yeah.
I'm taking much longer than you guys should take on these problems.
Solve all the first, yeah. 4 layers. Yeah.
Okay, so it is 3:40, so we can probably get through one more big question if everyone can agree on a topic. Or just post some ideas, and whichever one has the most
Also, like,
email me. I'll get back to you. Friction is going to internal forces. All right, so let's say, let's just have a vote, I guess. Or can you do like, go ahead and propose an idea? Oh,
I don't technically remember how we started. I know it was through rain, but I just don't remember that now. It's been a while.
okay, so yeah, I can, before we can do one example after that, like a a different kind of problem, but I can just talk about the methods for solving internal forces. So basically, whenever you have internal forces, you're going to have some kind of truss, right? So something like this is a good example. So here we have a regular truss. We're going to say there's a support and a roller. And for the sake of it, let's say you're given all the dimensions. I'm not going to write them down. But it wants you to find internal forces for a member, for this member and this member. And let's say there's a load here, 8 kilonewtons. Whoops. And a load here of 8 kilonewtons. So what you would want to do first for a problem like this is you would actually want to identify that this is a zero force member. Taking a look at this joint shows us there's nothing applied here, so this must be zero force. And if this is zero force, this one here, through this transformation of shapes, we have this shape to prove that this is zero force member. And then we have this, but if this is zero force member, we can get rid of this. And we can see that these must be opposite and equal, like that. So this must also be zero force member at this joint. So we could go ahead and say that the second joint, or the second member they wanted us to solve for, was 0. So we could go ahead and mark that one as completed. For this one right here, what you would need to do is you would need to find your reactions, AY, AX, and you also have a BY here. You could take a moment at B, solve for AY. Once you have your AY, take your cut. You could do some of the forces in the Y direction using the vertical component of this cut member and your AY. That equation will let you solve for this member, and then boom, you're done. And internal forces for truss problems like this can be, it's just that method that I explained. You identify if you have any zero force members. We quickly found this one. And then if you're asked to find something that's not zero force, find your reactions, start taking cuts where you have a member you're trying to solve for. We had one here, so we did a cut like that. This member and this member are unknowns, and then those are your answers.
The multi-layer truss is always best to make a cut instead of method by joints.
When you have multiple members like this in this, like back to back, yes, you can do method of sections because it will be much faster, as opposed to going this joint to this joint to that joint to this joint. Like moving around like that takes way longer than you guys are gonna have time for. And so like this truss problem, I didn't write out any of the equations and stuff. And like I left a lot of the dimensions and numbers and stuff off to the side, but that problem I talked about in like 3 minutes. So like,
Yeah.
that's once again showing if I was writing this all down and just going through solving it, then it's not going to take you an hour to get through one problem like I showed. So that is the general approach for internal forces. So then we can do general approach for friction. So for friction, you're generally going to have an object, right? Resting on the ground. And that object is going to have some kind of force that you're looking to solve for, P. And it's going to have a weight. It's going to have a normal force. It's going to have a friction. These things move around depending on whether you're testing slipping or tipping. Slipping, you're going to need to determine this P while keeping the normal force in the center underneath the weight, because the normal force is going to directly oppose this weight. And tipping, you're going to have to move the normal force to one side, because as this tips, it's going to look like this, and all of the normal force will be there. You would then solve your equation with whatever you can find appropriately, sum of forces on y, sum of forces with x. You would compare the two different force values you get for slipping and tipping, and then whichever one is lower, that is the one that will cause impending motion first. And when you're doing belt friction, that same lower one is the one that you use when finding the value on the other side, right? Because you'll have something like this. This looks familiar, I hope. This P would be here, and this would be your T2. When finding this T2, you use the P that's going to cause impending motion first. That would be the lower one that you find between slipping or tipping. And again, I have a video that shows how to do this. If anybody has questions, if I get like multiple questions about this, I will send out a mass email to everyone with instructions. And I will be actively checking my email today because you guys have the exam tomorrow. So that's going to be how you can do friction. And we'll go over cables real quick, the methods for cables. So let's say you have some random cable like this. We'll say that this lines up for the sake of it, and we have this point, we got some weights going on. And we're given dimensions and stuff. So what we're gonna wanna do for a problem like this is recognize that cables and internal forces of a truss are almost exactly the same. The only difference is that we know that all of these cables are going to be in tension. It's already confirmed for us because that's how cables work. When you have a weight pulling on the cable, this is in tension. We have a weight pulling on the cable. This is in tension. This is in tension. Everything's in tension here. So what that means is that the way we can do this is we'll have our reactions, our AY, our AX. You solve for them as you need. We'll say dy, dx. If we need these, we solve for them. If we don't, you can ignore them. It's never going to hurt you to solve them if you can, but sometimes you don't need them. Solve this, like this one has it lined up. We could do a moment at A or a moment at D, solve for whichever one we want. Take that cut, say we solved for AY, sum of forces AY gets us this tension, move on. If we have all these dimensions, super easy. You can just go through the entire cable, doing some of the forces in a direction, getting your values, and you would take this cut, get this one, move on, take this cut, get this value.
When you said find the forces at AY, you get that component, that tension.
Yeah. So let's say we took the moment at D, we find AY. So AY is considered known at this point. We would do some of the forces in the Y direction for this cut. That would be AY and the Y component of this, and that's it. That lets us solve for this. Boom, that tension's known. We take our next cut, go over here, we have this. Some of the forces in Y is going to be AY, Y component, this weight, the unknown. Solve for that, boom, we're done. Once again, cut, AY, this tension, weight, this unknown, solve for it, boom, we're done. If they don't give you all the dimensions, that's when you have to start incorporating sine and cosine, trying to find angles, using what you have in the problem at your disposal. A good thing to know is that if you have AX and AY, or DY and DX, and nothing else going on is unknown, I'm going to say this TCD, label it C and B. In this case, TCD to solve for this unknown. It's also important to remember, sine theta and cosine theta, and also tangent theta. All three of these trig functions, this one is opposite over hypotenuse over adjacent. These three trig functions are going to allow you to find angles and distances that you otherwise wouldn't have access to because they're not given. So a common thing is that they would give you this distance from A to B and want you to find this distance. The rest of the problem doesn't really matter. You would want to draw an imaginary line, create a theta, and then using distances that you have and forces that you calculate, you can find, you can end up finding this value and add this value to this value. I have a problem in the first review session that goes over something exactly like this.
Then how would you use the, so then you just use whatever theta you get to find tension by just plugging it back into some of the forces.
Let's see, so that was method of joints, method of sections, friction, cables, pulleys. Probably, let's say we have a bunch of random pulleys, right? And let's say we have a bunch of random pulleys. That looks something like this. And let's say this is the P value we're looking for. This is attached to the ceiling. This is attached to the ceiling. And this is 100 newtons. And we know that this is attached here and that this is attached to the floor. And that I'm gonna need to add another one. I got 100 newtons here. And the thing about pulleys is that this is one giant cable. So this 100 newtons is 100 newtons inside there and here. Because this cable is just one cable. The 100 newtons tension in this cable is constant. Which means that if we're looking for this P, and we take this pulley right here where the cable we're looking for connects, and we have 100 on both sides, this must be 200. Because when you take this pulley by itself, like this, and you have 100 and 100 going down, and we're looking for this, some of the forces in the y direction is equal to 0 is equal to our unknown P minus 100 minus 100. So P must be 200. It would if you were coming this way. If we had, yeah, I'm gonna reverse it. So let's say we're given, let's say the problem wants us to determine the mass that a 100 Newton force could hold, right? So the 100 Newtons goes through here. It's 100 Newtons here. It's 100 Newtons here. Here, it's going to half it because we're coming in from the other direction. So here and here are both 50. And then the important thing to remember is that if it asks for mass, you have to divide your force by 9.81 in metric units or 32.2 in US customary units. Because the difference between force and mass in the question will matter. Like you'll get points off if you give the force instead of the mass. And same thing if it asks for force and you give mass, it will be points off. So remembering the difference and making sure your answer answers in talk about one more pulley thing because it is 3:58. So the last pulley concept that I want to talk about also relates to a problem I already did in the first video. But anytime you have a pulley in a problem, this is the exact problem that, or the exact like shape of the structure I did in the first video. So all this means is that, oh, when you take this frame apart from this frame and you model it as one thing, you're gonna have 100 and you're gonna have 100 like this. Because when you take your cut and you get rid of, and you pull, I shouldn't say take your cut, when you pull this pin and you remove this section and you only look here, this cable is still here. So you have 100 on both sides. And that's how pulleys can be applied in frame problems. So any questions on everything I just said? I know that was very fast, but I wanted to include as much in the end of it as I could. I'll take some questions, and then if there are, once we finish through the questions, then good luck, guys.
I think I'm good. I'm fine.
All right, any questions from the Zoom? Nope. All righty. Yeah.
Thank you.
Oh, you're welcome, guys. You're welcome, man. And like I said, any questions, email me. I'll get back to you as quick as I can. I'll be at my computer all day for the rest of the day.
Okay. I have a question, but it's like not for like people on Zoom.
Okay. Sure, we can talk about it. Thank you. You have a great day as well.